Hello, Honors Chemistry, and welcome to Chapter 9, Sections through 9.3. All right, so things to take note of. So this figure is in your guys' book, and it's something that you guys should be kind of familiar with, right? You guys have all seen, I assume, at some point, right? Sunlight, right, as it diffracts through a prism, right? And we end up with a rainbow of colors, right? Super important to note here, right, that this would be referred to as a continuous spectrum. Right? In that when we look here, there is no break. It's not like there's red and then orange, right? It's red and then all the shades that carry it through to yellow, right? All the different shades of orange, and then all the shades of green that happen between yellow and blue, right? So forth and so on. In that there is every single possible wavelength represented here with no breaks, which is why this is called a continuous spectrum, right? So make sure that you have that vision in mind and you hold on to it because we're going to contrast it to something else, a huge discovery that leads us to the Bohr model later, okay? So anyway, continuous spectrum, important in science. All right. Then comes the electromagnetic spectrum. Important things to take away here. Like it says in your book, or in your outline, you're not expected to memorize that gamma rays are 10 to the negative 11th meters in terms of wavelength, right, and less, right? But you should know that it's gamma, then X, then UV, then visible, right? So note here is where visible falls, right? In between ultraviolet, where ultra means what? Right, beyond violet, right? And infra means what as a prefix? Less or below, right? So infrared is just below red, which is right here, right? Ultraviolet means just beyond violet, and violet is right there, right? Which then goes back to that mnemonic that you guys all learned back in grade school somewhere, right? About Roy G Biv, right? As in your color scheme there, right? So then that's how the visible spectrum fits in there, right? And note that the number of wavelengths represented by the visible spectrum is really small, right? As in our eyeballs can only perceive a tiny, tiny, tiny portion of the electromagnetic spectrum compared to what's out there, right? Which makes sense, right? Because if we could see the waves that are constantly bombarding everywhere around us, that'd be weird, right? Because I mean, if you stop to think about what all is encompassed in here, right? I mean, it's literally everywhere all the time, okay? So anyway, electromagnetic spectrum, things we should know. Finally, that brings us to that little section towards the end of 9.3 labeled video notes, okay? So your book does a very qualitative assessment of light, wavelength, and energy, right? Obviously, you know, this is honors chem. We want to make sure that we understand those relationships on also a quantitative level, right? So here are the equations that relate those pieces of information, right? So equations you need to know include C equals lambda nu, where C is, hypothetically you know this from middle school, speed of light, which is 3 times 10 to the 8th meters per second. And then we have lambda, which is wavelength. Now, if we think about C, so C is a constant. That is the speed at which all electromagnetic radiation moves through space, right? So space means what kind of environment are we talking about? Right, hypothetically a vacuum, right? As in there are no other atoms present, right? But we sort of approximate that to be its speed everywhere all the time, okay? So the speed of light is approximately 3.0 times 10 to the 8th meters per second. That being the case, what then must the unit be for wavelength? Right, meters. And then that leaves us with nu, which is the frequency of light. So wavelength, going back to what's in your book again, right? That is crest to crest, right? Or trough to trough, however you'd like to look at that, right? Frequency, its unit must be what based on the fact that that's meters per second? Right, 1 over seconds, which is symbolized as hertz, right? So just like when we see capital M, you know, capital M means moles per liter. When we see hertz, we know that hertz means 1 over seconds, and we should probably just go ahead and rewrite it so that we were more likely to use it correctly. Where hertz are the number of waves that pass in a 1 second window. So for example, if we put a time label on this of 1 second, hertz would be how many waves happen in 1 second, okay? All right, so C equals wavelength times frequency. based on that equation, what kind of relationship do wavelength and frequency have? Right. So now from a math perspective, right, you can see it in the picture also, but we can see that as one of these variables goes up, the other one must, right, the other one must go down in order to maintain C as a constant. Yes? All right, next equation. E equals H nu, right, where E is the energy measured in what? Right, joules. This is frequency, again, the same frequency we talked about in the previous equation. Here, though, we have Planck's constant, which is 6.626 times 10 to the negative 34th joules times seconds. Okay, and again, it is a constant, which means it doesn't change, which means you memorize it and then you always know it, which means that now we can also deduce a relationship between E and nu. Yes? And what is that relationship? Right, they are directly proportional, right? As one goes up, the other one must go up if Planck's constant is to remain constant. And then, things to note here, right, is that all of these are per photon, right? As in we are talking about the wavelength of a photon, the frequency of a photon, and the energy of a photon, right? So if we wanted to be super duper thorough, right, we could say that the energy is joules per photon, right? You know, just something to think about. So then, using all of your fantastic math prowess, you should be able to look at these two equations side by side and come up with a third equation that relates E and wavelength. Take a moment, figure that out, and bring that to class tomorrow. All right. Okay, yep, I think that's it. All right, thanks for listening. Be good, and I will see you soon. Bye.